I know Evgeny for many years, and we worked together and wrote many papers. No, as a mathematician, had a stronger influence on my work than Evgeny. So when I received an invitation to speak in this event, at first I thought it would be very easy for me to pick up a particular subject for the talk. I just thought I could talk on any of our many joint papers. But then I started to reminisce, and I felt that I cannot really choose one single topic for this talk. So I decided to give a talk about everything that we did. But everything, of course, is also impossible. So it will be kind of a collection of memorable moments of my joint work with Evgeny Khukhro done in the past 30 years. Okay. Our first contact with Evgeny happened in the late 80s of the past century. I was a student in Sverdlovsk, now Ekaterinburg, and he was already a well-known group theorist working in the prestigious Mathematical Institute in Novosibirsk. And in particular, he was rather famous for his results on almost regular automorphisms. And I also worked on automorphisms, so our contacts were very natural. Once I mentioned to him the following question: let G be a finite group admitting a fixed point free for group of automorphisms. Is the derived length of G bounded by some constant? This was a natural question. We just had a discussion about what happens to a finite group if it admits a fixed point free automorphism. So, as Evgeny just mentioned, if the automorphism is of prime order, the group is nilpotent of bounded order, of bounded class, sorry, and so in particular, its derived length is bounded by a function depending only on the order of the automorphism. Now, if finite group admits a fixed point free automorphism of order 4, we have a theorem due to Kovács that says that the group is central by metabelian. So in particular, its derived length is at most 3. And if the fixed point free automorphism has arbitrary order, say n, then it's an open question whether the derived length can be bounded in terms of n only. Now, my question here was about 4 group. It's but basically the same question, just what happens if the acting group is not cyclic? Strangely, I think this was never addressed in the literature at the time. But Evgeny answered it in the negative, just in the same day. And in his solution, he used Leerings and the Baker-Hausdorff formula. And this was my first encounter with the Leering methods applied to group theory. And since then, this motif is central in my mathematical work. So for a few years, we just had some discussions, sometimes just physically writing letters to each other. Then our first joint paper came in 1995. We worked on it in 1994. It was about locally finite groups of prime exponent. I just recall that the group is said to have exponent E if every cyclic subgroup of the group G has order dividing the given number E. And normally E is supposed to be the least number with this property. It was known that locally finite groups of prime exponent at least 5 do not have to be soluble. Razmyslov gave examples of locally finite groups of prime exponent at least 5, which are insoluble. On the other hand, in our joint work, we obtained the following surprising result. So let G be a locally finite group of prime exponent P, admitting a coprime soluble group of automorphisms A, such that the centralizer in G of A is soluble. Then the conclusion is that G is nilpotent. This was rather surprising because it's already was well known that fixed points of coprime automorphisms have strong influence on the structure of the group G. But normally the influence is not that strong. Here is a centralizer just soluble, but the conclusions about the group G is that it's nilpotent. And well, I think this theorem is still an open problem if A is not supposed to be soluble. So if A is just an arbitrary coprime automorphism group, we just don't know if the same conclusion can be reached. Well, the proof of this theorem was mostly based on Lie techniques, and in particular, we established the following criterion for a Lie ring to be soluble of bounded derived lengths. So let L be n-graded Lie ring in which zero component acts ad nilpotently, say with index k. Then the ring is soluble and its derived length is bounded in terms of k and n only. And this extends the well-known Crick-Nin theorem that says basically the same, but in the case where L naught is trivial. Also for finite dimensional algebra.
Sorry, what's L naught?
But I'm talking about n-graded Lie ring.
So I see. Yes. So, sorry. Yeah.
It's the sum of
Sure.
groups, and yeah, the one that corresponds to zero is called is L naught here. Okay, so this was also known for finite dimensional Lie algebras due to Winter. But again, in Winter's results, there was no mention about derived lengths and whether it can be bounded. So this result was new at the time. Well, then, so this was our first joint work. At the time when we wrote it, I lived in Israel, and I think Evgeny stayed in Novosibirsk. And then our next paper came 5 years later in 1999. And by this time, I already lived in Brasilia, and Evgeny was in Cardiff. The result is that if E is a positive integer and P a prime, and suppose that an elementary abelian P group of rank at least 2, so non-cyclic elementary abelian P group, acts on a finite P dash group in such a manner that centralizer of every non-trivial automorphism from A has exponent dividing E. Then the conclusion is that the exponent of the whole group G is bounded in terms of E and P only. Actually, we started talking about this result even 10 years before that. But I think certain tools that were used in the proof just didn't exist 10 years before. So we had to wait till 1999. This really was very new, also in the sense that while the results about fixed points of coprime automorphism were abound, none of them really treated questions of exponents. So as results on exponent of finite groups in the context of centralizers of automorphisms, this was very new. This was also very new in the sense that it was the first time that the techniques developed by Zermanov and his solution of the restricted Birdside problem were used in the study of fixed points of automorphisms. Generally speaking, Lie methods were quite typical for the study of fixed points of automorphisms. In particular, the famous Higman theorem was proved using Lie algebras. But what Zermanov created, the techniques really drastically enlarged the area where Lie methods could be used. Also, the proof also used some other complicated tools, including the theory of powerful P groups due to Lubotsky and Mann, and also some results from Lie algebras due to Bakhturin and Zaitsev. So that was kind of beginning of new chapter in the study of fixed points. And after that, many other results were obtained in the same spirit. In particular, I would mention my results with Bob Guralnik obtained in 2001. And the result is almost like in the theorem with Evgeny. Just instead of the acting group of rank at least 2, now we need that A would be of rank at least 3. But instead, the exponent condition is imposed not on the whole centralizer of automorphisms, but on the derived groups of the centralizers. So if for every non-trivial automorphism from the acting group A, the centralizer in G has derived group of exponent dividing E, then the exponent of the whole group G is bounded in terms of E and P only. The proof follows the general line as was in the paper with Evgeny, but this also was technically more complicated. In particular, it seems the use of classification of finite simple groups is necessary to prove a result like that. But what is perhaps is more interesting, that work with Evgeny also started a line of research of centralizers of coprime automorphisms of profinite groups, of infinite profinite groups. So we say that automorphism of finite order alpha of a profinite group is coprime if its order is coprime to the order of any finite image of the group G. And say in 2002, I proved a kind of non-quantitative version of the theorem that was obtained in the work with Evgeny. So the result is that if an elementary abelian P group A of rank at least 2 acts coprimely on a profinite group G in such a way that the centralizer of every non-trivial automorphism is torsion, then the group G is locally finite. Of course, this uses the famous theorem due to Efim Zelmanov that says that any profinite torsion group is locally finite. But here we impose the condition of torsion only on centralizers. And here we don't ask centralizers to be of finite exponent. So this is really kind of non-quantitative variation on the same topic. Well, here, of course, we just use compactness. And in some sense, compactness really can substitute finiteness. Okay, there are other results. There are rather many results in the profinite case. I especially like the following theorem that was relatively recently obtained in a joint work with Evgeny and Christina Achari. And it says that if a profinite group G admits a coprime automorphism alpha of prime order, such that every fixed point of alpha is a right angle element, then the group G is locally nilpotent. This is pretty easy if the group G is finite. So why it's easy? Because in finite groups, right angle elements belong to some term of the upper central series. And it follows that if G here is finite, then alpha x fixed point free on the quotient over some term of the upper central series. And now there is also a classical theorem due to John Thomson that if a finite group admits a fixed point free automorphism of prime order, then it is nilpotent. So here we get a situation when quotient by the center is nilpotent. And then of course it follows that the group G is nilpotent. So this is for finite group, but for profinite groups, this absolutely doesn't work. This line of argument only produces that the group G would be pro-nilpotent, and locally finiteness is a much stronger property than pro-nilpotency. So the pro-finite case is complicated. I believe that Christina Achari in her talk will give you more details about this theorem. I will now move on because I want to talk about many things that we did with Evgeny. So in the years 2009 to 2011, that is Evgeny, Natalia Makarenko, and I worked on Frobenius groups of automorphisms. So these were very happy years, and I'm very happy even when I just reminisce about those years. So, but first, what is a Frobenius group? I just recall that Frobenius group is a finite group which is a semi-direct product of F by a subgroup H. such that H acts on F in such way that for every element, non-trivial element from H, the centralizer in F is trivial. It's known that F here is a nilpotent group and of class bounded in terms of the order of H. H doesn't have to be nilpotent, but still we have a lot of restrictions on the structure of H. In particular, all Sylow subgroups of H must be either cyclic or generalized quaternion. So a double Frobenius group is a triple product GFH, such that both the product GF and HF are Frobenius groups. So Mazurov raised the following question. Let GFH be a double Frobenius group. Is it true that the nilpotency class of G can be bounded in terms of the order of H and the class of nilpotency class of the centralizer in G of H only? You know, there is some miracle already in this question. At first, I couldn't understand it, couldn't believe it. Now, let's look again at the definition of the double Frobenius group. There are conditions that GF is in a Frobenius group and FH is a Frobenius group. There is no assumptions about action of H on G. Of course, H acts in some way on G, but it doesn't say much about the action. And yet, Mazurov here suggests that the structure of G can be bounded solely in terms of H and its action of G. That was miraculous. But then, really, the first substantial evidence that the answer to this question might be positive was obtained by Evgeny in 2008. And he proved that if the centralizer in G of H is abelian, then really G is nilpotent of class bounded only in terms of the order of H. So that was already strange, but of course this was a strong incentive for us to start work on this. And then we three, Evgeny, Natalia, and myself, we worked on this and we solved this problem in the positive. So indeed, if GFH is a double Frobenius group, then the nilpotency class of G is bounded in terms of H only. I now don't remember why Evgeny dropped from the list of the authors of this result. That happened in the last moment. We all worked together. But once this was solved, actually better results were obtained. And that was a paper where all three of us are authors. And so we proved that if a finite group G admits a Frobenius group of automorphisms, FH, with cyclic kernel and complement H of order Q, such that the centralizer of F in G is trivial and centralizer of H in G is nilpotent of class C, then G is nilpotent of class bounded in C and Q only. This precisely like what Mazurov suggested, but just this is the hypotheses in this theorem are weaker than what was in Mazurov's question. Here, the product GF doesn't have to be a Frobenius group. You remember, Frobenius group is a group where the centralizer of every element from F in G is trivial. Here we only require centralizer of the whole group F in G to be trivial. So the hypothesis is weaker than in Mazurov's conjecture. Still, the conclusion is the same as in Mazurov's conjecture. As byproducts, we also obtained other results that roughly shows that the structure of G is bounded in terms of H only. The proofs of this are rather complicated and mostly really theoretical. And I believe that Natalia Makarenko in her next talk will give you more details about this. I will now move. And just from 2014, when it's just was a coincidence, Evgeny just started his work in Lincoln. And also he started his frequent visits to Brasilia. We had good grants at that time. We worked a lot on many subjects, and many new ideas were born in that period. I will describe just some of the obtained results. See, various notions related to the length of a finite group have been introduced in the context of the restricted Bernstein problem. So given a finite soluble group, the fitting height of G is the minimal length of a normal series with nilpotent quotients. And it's clear that the group is nilpotent if and only if its fitting height is 1. And very often, once fitting height is bounded, we also can reduce the problem, a certain problem, to the problem on nilpotent groups. This was instrumental in the eventual solution of the restricted Bernstein problem, for example. But when the group G is non-soluble, we need something else. We need so-called what we adopt insoluble length of a finite group. So every finite group G has a normal series, each of whose factors is either soluble or is a direct product of non-abelian simple groups. In our paper, Evgeny and myself, we defined the insoluble length and denoted it by lambda of G as the number of insoluble factors in the shortest series of this kind. Actually, I think minimal number of insoluble factors in any series of this kind. Well, implicitly, the concept of insoluble length was already used in the famous Hall-Higman paper of 1956, where they reduced the restricted Bernstein problem to the case of finite P groups. In our paper of 2015, we obtained many new results on lambda of G. In particular, we proved that the insoluble length of a finite group cannot be bigger than the maximum fitting height of soluble subgroups of G. This and other results then happen to be very useful in many situations. But all results related to this parameter, lambda of G, one way or another depend on the classification of finite simple groups. In particular, even that result here depends on validity of the so-called Schreier conjecture. Schreier conjecture was that for any non-abelian finite simple group, the outer automorphism group of S is soluble. And then the conjecture was confirmed only using the classification of finite simple groups. I think there is still no proof that wouldn't use classification. So in what I'm going to quote now, whenever I say about results involving insoluble lengths, they all depend on the classification. Okay, also I'd like to recall that generalized fitting subgroup of a finite group is the product of the usual fitting subgroup and all subnormal quasi-simple groups. And the group is quasi-simple if it is perfect, that is, it is equal to its derived group. And the quotient by the center is a non-abelian simple group. So then we can define generalized fitting series of G, just starting with the first term would be just a generalized fitting subgroup. And then by induction, I plus first term in the inverse image of the fitting subgroup of the quotient G over the ith term of that series. And then the list number H for which the H term of that series equals to G is naturally defined as the generalized fitting height, we denote it by H asterisk, H star of G. Also note that the insoluble length of the generalized fitting subgroup is at most 1. It's not equal 1. Here is wrong. It should be at most 1. And therefore, insoluble length of a group G is always at most its generalized fitting height. So the results, we had many results involving those parameters. I will just mention two of them. First, about factorizable groups. So if a finite group G can be written as a product of two subgroups A and B, then it's natural to expect that restrictions on the structure on A and B implies certain restrictions on the structure of G. That's very natural, and indeed, I would like to mention in this context the following theorem proved by Cazzolo, Yabara, and Spiga. Let G be a finite soluble group factorized by its proper subgroups A and B of coprime orders. So let D be the derived length of B. Then the fitting height of G is bounded in terms of fitting heights of the factors A and B and the derived length of one of the factors. By the way, it's known that you cannot bound the fitting height of G in terms of fitting heights of A and B only. That's impossible, so this is a good theorem, and in a way it's best possible. But we kind of extended this theorem to the case when the group G is not soluble. But first, let's see, it's natural to ask if G is not necessarily soluble, and if G can be written as a product of its two proper subgroups of coprime order, is it true that the insoluble lengths of G can be bounded in terms of insoluble lengths of A and B? And the answer to this particular question is no. Indeed, if we consider G to be the simple group of order 60, the alternating group of degree 5, then we just observe that G is a product of two subgroups, one of order 12, the other of order 5, and so both are soluble. And then if we consider the iterated Riesz product of G with itself, we obtain a group of arbitrarily large insoluble lengths, which still would be a product of two soluble subgroups, a whole to 3 group and a seal of 5 subgroup. So the factors both would be soluble, that is lambda of the factors would be 0, but the insoluble length of the group G is arbitrarily large. So the answer to this particular question is no. And so this makes it even more interesting that about the generalized fitting height, the answer is actually yes. So suppose that G is a product of its two subgroups of coprime order. So first about the insoluble length, then the insoluble length of G is indeed bounded in terms of the insoluble, in terms of the generalized fitting heights of the factors H star of A and H star of B. And we gave an explicit formula that bounds the insoluble length in terms of the generalized heights of the factors. Quite possibly this formula can be improved and made even linear, but for now that's what we have. And also about the insoluble length. Yeah, sorry, this is about insoluble length, and then about generalized fitting height. Just I recall that, sorry, here in the theorem due to Cazzolo, Yabara, and Spiga, as I mentioned, you cannot bound the fitting height of G in terms of fitting heights of factors only. You also need the soluble, the derived length of one of the factors. And the same happens when you bound the generalized fitting height of G in terms of the factors. So if G is a possibly insoluble group, which is a product of two subgroups of coprime orders, we just note that at least one of those subgroups have odd order, and so it is soluble by the Phi-Thompson theorem. So at least one of them is soluble, let's say of derived length D. Then the generalized fitting height, H star of G, is bounded in terms of D and the generalized fitting height of the other factor. Okay. Another classical results on length of a finite group is due to John Thomson, who proved the following famous theorem. Suppose that a finite soluble group G admits a soluble group of automorphisms A of coprime order. And suppose that the order of A is the product of n primes counting multiplicities. Then the fitting height of G can be bounded in terms of this n, the number of primes dividing the order of A, and the fitting height of the subgroup of fixed points of A. So Thomson proved this in 1964. And after he did, a lot of related work was done. Really, a wealth of results pouring in. In particular, in 1984, Torell obtained the best possible bound for the fitting height of G. He proved that it's, okay, again, the bound here is linear. But in a joint work with Evgeny, we extended this to the case when G is not necessarily soluble. And we proved the following result. Suppose that a finite group G admits a soluble group of automorphisms A of coprime order. Then the generalized fitting height of G is bounded in terms of fitting height of fixed points and the number of prime divisors of the order of the group A. So this is exactly like in Thomson's theorem, just but our result applies to all groups, not necessarily soluble. And we also produced an explicit bound for the fitting height of G, and it's also exponential, like in original Thomson result. And quite possibly it can be improved, and perhaps it should be made linear. Who knows? That's quite possible. Also, we proved related results about the insoluble length. And it happens that if a finite group admits not even necessarily soluble, but it must be soluble, coprime group of automorphisms A, then the insoluble length of G is bounded in terms of insoluble length of fixed points and the number of prime divisors of A counting multiplicities. Why we don't need to impose the conditions that A is soluble here? It's just very simple. Just by Phi-Thomson theorem, either G or A is soluble. So automatically we have this conclusion without really requiring any of these groups to be soluble. And again, the bound that we produce in the proof is exponential, but we think that, at least I think the improvements of these bounds are eventually likely. Okay, but I will move on. We worked on many things, including so-called angle groups. So I'd like to mention, to recall that a group is angle if for every pair of elements, X and G, all the long commutators, if G are repeated here sufficiently many times, are eventually trivial. And clearly that any locally nilpotent group is an angle group. Wilson and Zelmanov proved the converse for profinite groups. And so they proved that angle profinite group is locally nilpotent. In general, it's known due to, for example, there is an example of Golod that says that an arbitrary group, even residually finite group, with this satisfying this condition doesn't have to be locally nilpotent. So this result holds only for profinite groups, but later Medvedev extended this to angle compact groups. And the class of compact groups is larger than the class of profinite groups. So So it's now known that every angle compact group is locally nilpotent. Now, we say that a group is almost angle if for every element G, there is a finite subset E of G such that for every X and all sufficiently long commutator with G repeated sufficiently many times belong to that subset. So more formally, we can define it as for every given an element G, for every element X, there is a positive integer such that all long commutators with n here bigger than n depending on X, all such long commutators belong to that fixed finite subset of G. So the angle groups, as I defined just in the previous slide, are precisely those for which we can choose that finite subset E of G to be the trivial subset. Then we just get the angle groups. With Evgeny, we published several papers on the structure of almost angle groups. We proved rather many results, and in particular, we proved that almost angle compact groups are finite by locally nilpotent. And so this provides an extension of the Medvedev-Wilson-Zelmanov theorem. So this is a stronger result than what we had before. Okay, and then rather unexpectedly, this result found an application to the problem on conciseness of finite groups. To conciseness of words in profinite groups. So just a few words about what was the problem. So given group word W, we define, and given a group G, we define the verbal subgroup of G as a subgroup generated by the set of all W values in G, whereas the elements G1, G sub K just run over G. And for example, if W is just a commutator, then the corresponding verbal subgroup would be the commutator subgroup of G. If the word is different from commutator, then the verbal subgroup in general is different. But it's clear for any word, we can define the verbal subgroup in any group. So a word is called concise if the verbal subgroup is finite whenever W has only finitely many values in the group G. And in the 60s, Philip Hall asked whether every word is concise. And indeed, it turned out that many important words are concise. This was proved after Philip Hall asked his question. On the other hand, the answer to Hall's problem turned out to be negative. The negative answer was obtained by Ivanov in 1989. He constructed a group G admitting a word W, which takes precisely two values in G. One value is trivial and the other is infinite cyclic. So the verbal subgroup would be cyclic. But then it was noticed that the group G is not residually finite. And then, so Hall's problem for residually finite groups remains open. In particular, it was mentioned in some publications by Andrei Haiken, Zapirain. And what's interesting, it was recently shown that this is really a genuine problem in the sense that there are words that are known to be concise in residually finite groups, while not concise in the class of all groups. So we have here an interesting problem for residually finite groups. And automatically it produces a problem also for profinite groups. But in the case of topological groups, the problem on conciseness admits an interesting variation. And let's say that the group word W is strongly concise if the verbal subgroup W of G is finite whenever G is a profinite group in which W takes less than continuously many values. And so the question is every word is strongly concise? You know, a profinite group has cardinality at least continuum if it is infinite. So profinite groups is either finite or it's very large. It has cardinality at least continuum. And so here the question is, if we have a word map, is its image also of cardinality either finite or at least continuum? So maybe it's purely topological question, but we do algebra here. It was shown in several works with Eloisa de Tomi, Benjamin Klopsch, and Marta Morigi that many words, including some short words given here, all multilinear commutator words are strongly concise. We also proved that all words are strongly concise in the class of nilpotent profinite groups. But in general, the problem remains open. In particular, we still don't know if the Engel words are strongly concise. But in my joint work with Evgeny, we actually proved that for every n, an Engel word is strongly concise in the class of finitely generated profinite groups. So we have here such a surprisingly strong conclusion about finitely generated profinite groups. If such a group contains less than continuously many values of the n-Engel word for some n, then the whole group is finite by nilpotent. So really from a relatively mild hypothesis, we deduce a rather strong conclusion here. G is finite by nilpotent. Well, this paper with Evgeny didn't go unnoticed, but this is more like a joke. I even received an email from mathematici Nachrichten that says, congratulations, your work is one of the most cited papers. So that's how I became famous due to my work with Evgeny. And so thank you, Evgeny, and thank you, everyone.